Hello and welcome to CircuitLab. My name is Mr. Burleson and this is practice 2 of 15 of CircuitLab. Last practice we talked about the basics of electricity and how all matter is made up of atoms, and those individual atoms are made up of protons, neutrons, and electrons. And the flow of electrons from the valence shell, or the places where the electrons would normally be at, also referred to as holes, is what makes up electrical current. We also talked about V equals IR, or Ohm's law, the most important formula for you to know. The key thing to remember is that voltage is equal to the current times the resistance, and that using that law you can determine the current, the resistance, if you know the other two. We talked about how a circuit is a loop-shaped path through which electrical current travels from a source around and back to ground. A short circuit is a circuit with a zero or low resistance path. Please remember that a short circuit is very dangerous and can drain your batteries and or even start a fire if it melts the wires. So let's talk about static electricity. Static electricity is electricity that does not flow. In other words, it is static charges. It has a voltage, so think of it as being water that's not flowing but has a lot of pressure. It has zero current, so in other words, the thing that makes it static is that the charges aren't moving. So it's caused by an imbalance of electrons in two materials. So if you take two glass rods, which both happen to have the same number of excess electrons, they will actually repulse each other because the like charges repulse or push away from each other. Also, by the same token, if they have fewer electrons and so they're positively charged, two positive charges will push away from each other. So please keep in mind that if you look at, let's say, wax normally has excess electrons. So in this case, wax would have a negative charge and would push away wax, whereas like a wool cloth, okay, will actually have fewer electrons or an excess of positive charges. Okay, so the wax is actually attached to the wool cloth. If we put a wire between the two, we would actually have electron flow, or we would have a current that flows from one to the other. It's important to know the way glass, wax, wool, and silk interact with each other. And the reason why that's important to know is because these are quite often used to recreate classical electrostatic experiments. So, how do these electrons move or conduct? Okay, they need a conductor, which is a material which allows electrons to easily pass. We talked about that in the previous practice. The materials that they can pass through easily are called conductors. Materials that they can't pass through very easily are called insulators. You'll notice we gave a lot of examples last time, and then the other thing is that if you go to the homework generator and go to the material data sheet, there's examples as well. A lot of times people like to think of it is, what if these positive charges or these electrons are like marbles and they're going through a tube? And the reason why is that you'll notice that the marble on the left, when it goes in the tube, it pushes out the marble on the right. It's not the same marble, okay? And that's something to keep in mind, that when you're counting the number of charges that are going past any one location, it's because there's only so many charges that can fit through that conductor, but they're not necessarily the same charges. It's sort of a statistical model. So a circuit is a loop-shaped path by which electrical current flows around. So if you look in the right-hand side here, we have conventional current flow, which flows out of the positive terminal all the way around through the light bulb and back into the negative part of the battery. However, keep in mind that's the conventional current flow. The electron flow, or the real current flow, actually flows the opposite direction. Please note it has to complete the circuit or else it's called open, in which case if the switch is left open, no current can flow through it and it shuts it off. This is how you turn off a light in a house. Now a short circuit would be, what if we didn't have a light bulb there and we just had wire around there? Well, V equals IR, and if R is equal to 0, but our voltage is something, the current actually goes to infinity. While that's not practical, it still can go really, really high and cause all sorts of problems and be very dangerous. So what direction does the current flow? The current flows from the positive terminal of the source to the negative terminal, or ground. Okay, so think of it using that marble situation. Think of it as being a hula hoop where the marbles are all going around. Okay, however, keep in mind electrons flow opposite to the way of conventional current, honestly, because Ben Franklin guessed wrong as to which way electrons flowed. He really did some great experimentation, and he really had no way of knowing. But just keep in mind that if the circuit is open, no current flows. So how does this compare again to water? Remember we talked about the situation where you have a pump, you have a reservoir, and you have a lower reservoir. Okay, and you'll notice in the diagram here, as we pump, we increase the water pressure, and then when the water comes out of the reservoir, okay, it goes from a high pressure down to a low pressure and then back into the pump. This is very, very similar, if you will, to the way that that an electric circuit works. Again, it has to be a circular pattern. So let's talk about how to identify batteries. All batteries are going to be direct current. They're usually denoted by their voltages. Very common ones that you'll find are 1.5 volts, 3 volts, 6 volts, 9 volts, 12 volts, and 24 volts. Okay. Generally speaking, if I look over on the right hand side, that D cell at the top, the Duracell Plus, that's going to be a 1.5 volt battery. Most of those types of batteries are all 1.5 volt. If I look off to the right with a Panasonic battery, that's going to be a 9 volt battery. That's a very standard configuration for a 9 volt battery. And that's used a lot in smoke detectors and some electronics. If I look below to the larger, acid-filled batteries, those are probably going to be 12 or 24 volt batteries normally. And a 12 volt battery is quite often used in a car, and a 24 volt battery is quite often used in like a marine engine, like a boat. But let's talk about how to make measurements. Hopefully your coach or you have been able to lay your hands on a multimeter. That's sort of the common device. You can get them at Harbor Freight for very low costs, under $10. You can also get them at Walmart and several other vendors, Home Depot, Lowe's, etc. Multimeters can measure multiple things. They usually measure voltage, resistance, and current. Okay. Now, I will warn you, measuring current is a very dangerous thing to do. That's why you'll notice that you have to move your leads, where normally your leads are set up to measure voltage and resistance. And for all practical purposes, that's how you want to always have your multimeter set up. It's very safe, etc. Current, if you don't measure current correctly, you can damage your circuit, you can damage your multimeter. When we were in electrical engineering school, we didn't go through a single lab without somebody blowing an amp meter, blowing the fuse in an amp meter. So if we look over to the right, here's some of the standard parts of a multimeter. You'll notice that you have two leads, usually a red and a black one. And the black one you will put in the COM port on the multimeter, okay, through the plug. Think of this as being the negative terminal, and it's always going to be the same. That's why they call it common. However, the red probe, you'll hook it in to where you can measure voltage or resistance, and sometimes you will actually unplug it and plug it in where you can measure amperage. Now, the key thing I want you to keep in mind here, generally speaking, you will never do this. And the reason why is because when you measure amperage, if you accidentally short the circuit, it will blow the fuse. It will potentially damage batteries. It will potentially damage your circuit. It will potentially damage your multimeter. Okay, so that's why it's so dangerous. However, the other thing that you'll notice is that if you look at the multimeter, you can set the dial normally to measure DC voltage, which you'll notice here is designated in the lower left-hand corner where it's V with two straight lines. AC voltage, where it's a V with a sinusoid in the upper right. The very top is resistance, and they give that by the ohm signal. And then the top right would be AC amperage, alternating current amperage. Again, also very dangerous to measure. And in the lower right hand corner is DC amperage. So when you plug your leads in as shown here, so I've got it plugged into the volt ohm configuration, I can now measure voltage, I can measure resistance. And what you'll notice here is that I want to see if my battery's any good. So what I do is that I set it to DC voltage because all batteries are DC. And then I measure the terminals of my 9-volt battery. And I see that it's got 8.754 volts, which means, it's still working. Okay. If it came back with like 3 volts, I need to replace it. If it came back with 0 volts, it's probably a broken battery. Okay. Now, the other thing is that in that same lead configuration, I can then switch it over to measure resistance, and I can measure the resistance of a resistor. And you'll notice here I've got a resistor. It's a carbon composition resistor, and it comes out to about 61.28 ohms. Most of the time, your multimeter will what they call auto range. So if it's in mega ohms, it'll put the little M ohm symbol. If it's kilo ohms, it'll put the K ohms symbol. And if it's not, it'll just put the ohm symbol. Okay? Never use voltage AC or measure voltage amperage DC. Okay? Because, or amperage AC, because you're not going to be doing AC circuits. That's not allowed. AC, as we covered last time, is a little bit more dangerous. The other thing is try to avoid ever using amperage DC or amperage AC, regardless, because it's a little bit of a dangerous type of measurement. If you accidentally configured the leads to measure amperage and I plugged it into that battery, I would fry the multimeter or at least blow the fuse. And so therefore, whenever I'm running an event, I always put a little piece of tape over the port so that you can't even configure it to measure amperage. Now, one of the first things you're going to want to do most of the time is calibrate your multimeter. So what you do is that you set it up to measure a resistance, and then you touch the two tips of the leads together. Now, if in this case I get a half a ohm or 0.493 ohms, that means that that's how much resistance I have in the entire circuit. It might be from the leads, it might be from something internal or whatever. So I know I need to subtract that out any type of ohm or resistance measurement I make. Now, a half a ohm is a really small amount of resistance, and if I'm measuring something in mega ohms, it definitely will have 0 impact. However, if I don't touch those two leads together, or if something's broken inside the leads, it'll be an open circuit. Now, every multimeter displays open circuits differently. In this case, it says OL Okay, I've had it blink. I've had it say open. I've had a lot of different ways of finding out. So you really have to practice a little bit with your multimeter. So let's say if I'm required to measure current, okay, the best way to measure current. Let's say I want to measure current. I could, if I wanted to see how much current from this 9-volt battery goes through this light, this is how I would measure current. I hook up the lead into the amperage port, and then I put it in series. Okay? And now you can see how the current flows from the battery through the multimeter, back through the light, back into the battery. Okay? Now, as long as there is enough resistance, and there usually would be, on that light to prevent this from being a shorted circuit, it would actually be okay to do it that way. However, given the fact that so many things could go wrong, like let's say there's a short in the light bulb or something like that, and it could cause problems, that's not the way I would actually measure this. The way I would actually measure it is I would measure the voltage on the light bulb, and then I would take the light bulb out and I would measure the resistance. And if I had the voltage and the resistance, remember, I is equal to V divided by R. Okay, so it's always better to measure the voltage and resistance and calculate the current. So here's some of the points I want you to remember. Try to measure voltage and resistance because a multimeter will act as an open circuit generally. It will never blow a fuse no matter what comes on. No matter if it's too high a voltage, it'll just shut off. If it's too low voltage, it won't care. When measuring current, the multimeter acts as a short. Okay, so make sure that there is a load because you do not want to complete the short. The voltmeter schematic is usually shown by a V for a voltmeter and an A for an ammeter. But the thing that I want everybody to keep in mind here is that sometimes they just write voltmeter or write ammeter, and there's probably a half a dozen other symbols that they will use. The other thing to keep in mind is know your metric prefixes. Okay, resistance for a lot of our stuff is going to be in kilo ohms, which is thousands of ohms, or mega ohms, millions of ohms. A lot of times when we're doing stuff on pen and paper or pencil and paper, we will ask in ohms just because that makes it a little bit easier. Keep in mind that voltage is the same way. You could have millivolts, which is a really small voltage, or you can have megavolts, which is millions of volts. And so the key thing to keep in mind is know your metric prefix. Should be something that is in your binder, because let's face it, if I tell you that something's milliamps, that's 10 to the minus 3 amps. If I tell you something is nanofarads, okay, that's 10 to the minus 9 farads. Okay, and so that's what you need to know how things go back and forth. So for the practical, have your coach and teammates gather up different types of batteries. Be able to identify all the parts of the batteries, be able to identify quickly the voltage, positive, negative terminals. Set up some simple circuits with a switch. Then everybody sort of rotate around and make sure you know the direction of the current, both the conventional and the real current. Make sure you see with a switch that a break causes an open circuit, and then it will shut everything down. Describe what a short circuit would be, but never ever demonstrate because it's dangerous. And then make measurements with the multimeter so you can measure all the voltages. And then remember, if you're measuring the resistance, you quite often have to remove at least part of the element so that you don't accidentally measure the resistance while it's energized or while it's in parallel with something else. For homework, I'd like you to use the internet to find 2 ways to remove static electricity and explain how they work. In other words, explain how the charges are mitigated. Look for hair and clothing suggestions. These are very common types of questions that are asked on tests. Make a list of at least 10 conductors and 10 insulators. And try to do something more than just look at the list that's been provided to you in the homework generator. And also do sheet homework generator level 1 VIR. Thank you so much.